Hello, ladies and gentlemen. For one day only, it's the mathematician with mutton chops. Or actually, I don't know if these are long enough to be mutton chops or sideburns or whatever. I've been slowly shaving in between each question. We're going to continue on with the 2011 Galois paper. I should be clean shaven by the next question, but we're up to question number 3. So you can actually go back and see what I look like without a mustache, I think, in the previous video. Alright, so question number 3. In the rectangle ABCD, P is a point on BC so that APD is 90 degrees. Alright, so we have our 90 degrees shown here. TS is perpendicular to BC with BP equal to PT, as shown. Yeah, we got that shown as well. PD intersects TS at Q. There it is. Point R is on CD, so that RA passes through Q, and in triangle PQA, we have PA equals 20, AQ equals 25, and QP is equal to 15. And that makes sense to me. I see a right angle, and 15, 20, and 25, these are numbers that I associate with a Pythagorean triple. Okay. So we're probably going to need to redraw our picture again, just so we can put marks all over it and figure out side lengths and angles and everything. But let's take a look here at the questions. A, determine the lengths of BP and QT. Okay, so there's BP, and there's QT. Alright, so once we figure out BP, we'll know what PT is, and then that's another right angle, so we should be able to use the Pythagorean Theorem to get QT out of there. Show that PQT and DQS are similar. Okay, well, they both have right angles. And these two opposite angles should be equal. So we're asked to show corresponding angles in these two triangles are equal. I don't think that'll be particularly difficult. Okay. C, determine the length of QS and SD. Well, once we have a similar triangle, and in part A, we will have figured out what PT and QT are, so we should probably be able to work it out. And then finally, D, show that QR is equal to RD. So we'll either calculate both of them out separately, or possibly show that QRD is an isosceles triangle. So that's our general game plan. We've read through all the questions, so we know where we're sort of heading. We're trying to figure out different values and then lengths and angles in this rectangle here. So how about we redraw our picture? That's always an excellent idea. Actually, you know what? I'm going to skip over a page just because I don't want to have to keep flipping back to refer to this picture. I'd like to get at least 2 pages out of one picture. Alrighty. So we know we have a right angle up here. And these two angles are equal. That's a right angle, that's a right angle, that's a right angle. Got a 20 here, a 25, and a 15. And this line just keeps going up here. Alright, let's label some things. We have a B here, A, D, C. This fellow in here was Q. That's R, S, and I think T was up here. Okay. And point P, that's the other one. Point P is up here. So the first thing we're asked to do is figure out BP and QT. On this side length here was also 16. So we notice we got a right angle here in this triangle. So we're going to probably be using the Pythagorean Theorem a lot. And so that's if you have a right angle triangle, just in case you've never seen it before, we'll just briefly touch on it. If we have a right angle triangle, the sum of the squares of the two legs are equal to the square of the hypotenuse, the longer side. So by Pythagoras, 20 squared, which is the longer side, AP, is going to be 16 squared plus BP squared. So we can grab our calculator. That's going to be 400, 256 plus BP squared. We can rearrange here. 400 minus 256, that's going to be 144. So 144 is BP squared, and then we can square root both sides. We get 12 is equal to BP. And once we know that one, we know that PT is also equal to 12. So we've added in some brand new information. This is 12, this is 12. And now look at this, I have another right angle triangle here. PTQ is also right. So by Pythagoras, or by the Pythagorean Theorem, or however you want to say it, we know that 15 squared, because that's the longer side, is going to be equal to 12 squared plus QT, which is the one we don't know, squared. That's 225, 144 plus QT squared. And if we subtract both sides by 144, we'll get 81 is QT squared. Doesn't take too long to figure out that QT is equal to 9. So let's add in that piece of information. Okay. Well, that does it for part A, because we asked for BP, which we now know is equal to 12, and QT, which we now know is equal to 9. Alright. So at that point, I'd make a little therefore statement, put the letter A beside it if we were doing this real serious-like, because we've solved part A. So B part, show that PQT and DQS are similar. So we want PQT and DQS. We want them to be similar. So the only way to show similarity is to show that they've got the same angles in the right places. But they give us a little hint to show us that anyway. So I use the single squiggly line for similarity. I use double squiggly line for congruence. That means they have the same angles and the same side lengths. But we want similarity. So what do we need to show? Well, we need to show that each of the angles corresponds to the other ones that we want. So the way I figure out which angles we want are, you write the triangle's letters in order of the angles that are correspond. So PQT should be equal to DQS, and then I just shift over by 1. So QT, and then I put a P there, should be equal to, I shift over by 1, QSD, and then we shift over once more, TPQ should be equal to SDQ. Okay, so these are what I want to show. But these ones are equal to 90. That's given to us. So we just need to show the remaining two. Now, if I take a look right here, these two angles are going to be equal to one another. The reason being, TS and PD intersect at Q. So we'll just explain that over here. Right, TS and PD. And opposite angles at an intersection are always equal. So if I have any two lines and they intersect, these two are going to be the same, and these two are going to be the same. That's true of any line intersection. So that tells me that PQT is going to have to be equal to DQS. So we just need to show the last one, which was TPQ is equal to SDQ. So the sum of the interior angles of a triangle is always 180 degrees. So TPQ is 180 degrees minus the other two angles. QTP. But of course, we just got through showing that PQT was the same as DQS. And we already noted that QTP is 90, and so is QSD. But those are the other angles in the triangle DPQ or DQS. So the remaining angle, which is SDQ, must be equal to the angle we started off with, TPQ. So since we've shown equality, for our three pairs of corresponding angles, we conclude, and you have to make sure you get the order of the letters right, because we write down the letters in a very particular way here to show similarity. DQS. Okay, and that's what we were asked to prove in B part. PQT and DQS are similar. Well, we just did that, and we did it exactly the way they asked. If there had been another way to do it, we probably would have wanted to only do it with the corresponding angles method, because that's the one they specifically talk about. Okay. So C and D, well, C, determine the lengths of QS and SD. So I'm sensing the similar triangle result that we just used will come into play. I'm also noticing that we already know what QT is, and ABTS is a rectangle. So that means ST should be 16, and we already know that TQ takes up a certain chunk of that 16. QS has got to be the rest. So I'll write that right now. So since ABTS is a rectangle, TS is equal to AB is equal to 16. But TS is QT plus QS. So that's 16 is equal to 9 plus QS, just by using part A. So QS is equal to 7. Well, that's one of the ones we wanted. Now we want SD. But once we know one of the side lengths here, we just figure out its corresponding side length in the triangle that we're similar to. And that should tell us the ratios of the other sides. We should be able to work the whole thing out. Okay. So from B, we know that PQT is similar to, what were they? DQS, I believe. Okay. So we know this is 9, this is 7, this is 12, this is 15. Okay. Oh, with this 7 here, just as a little side note, if we go back a little bit, there was another way we could have figured out what QS was. We have a 25 here, and so AQS is a right angle triangle. It's got hypotenuse 25, and its length AS will be 12 plus 12, again because it's a rectangle. So we'll have 25 and 24 here. 25 squared minus 24 squared is going to be 49, which is 7 squared. So that's another way you could have worked it out. So both ways are equally valid. So because they're similar, then the corresponding sides have common ratios. And we'll show what we mean by that when we go ahead and solve the question. There's Q, there's S. So QT, and we can read them off rather nicely. What I like to do is I like to write one above the other one. And this is where the order of the letters actually matters. Because here's PQ, here's DQ. So we should have PQ over DQ. The ratio of those side lengths should be the same as, well, here's QT and QS. QT over QS. And then the last one that's left over would be T and P over SD. So writing the letters out in the proper order to show not only does actually demonstrate the proper similarity, but it makes writing these ratios out really, really nicely. They're really, really nice. Now we know one of these. SD is the one we want. So that's the one we want. We know what TP is. And we also know that QT over QS, that's going to be 9 over 7. So QT over QS, that's TP over SD. That's 9 over 7 is going to be the same as 12 over SD. Well, we can sort of cross multiply. So 9 times SD is going to be equal to 7 times 12. If I want SD all by himself, and I do, I can divide both sides by 9. So now 7 times 12, I believe that's 84. But we have our calculator, so why not use it? 84, so 84 over 9, that's not an even division. But it's close. We can either write it in decimal, or I'd prefer personally to write it as a fraction. So that's 81 plus 3 over 9, so that's 81 over 9 plus 3 over 9. Both of these can be simplified. 81 over 9 is 9, and 3 over 9 is 1/3. So I'd say our answer should be 9 and 1/3. And of course you could read that off from a calculator. 9.333 repeating is of course just going to be 9 and 1/3. So we wanted QS, which is 7, and we could have figured that out 2 ways. And SD, which is 9 and 1/3. And guessing based on the structure of this question, we'll probably need these values for D part, but we're going to see that. So we got C, that's fine. Now we need to show QR is equal to RD. So we can either outright calculate them. How best to do that? Well, we have another right angle here at D. So ADR is a right angle triangle. We don't know its hypotenuse entirely. We do know what ASD is. So, something in two approaches. Either we give QR and RD variable names like X and Y and plug them into that Pythagorean triangle equation. So the hypotenuse would be 25 plus X is equal to, or squared is equal to Y squared plus whatever AD squared is. So that's a possibility. Or we can try and show that angle RQD is the same as angle QDR. That would also do it. So show it's an isosceles triangle outright, or just compute QR and RD. Either or should be fine. Just trying to think of a way to actually show it. Well, let's do both of them. So if we go the Pythagorean route, we'll need to use the fact that SD is equal to 9/3. But let's just try the angles. I'm just going to sort of draw a picture and try and chase some angles around here. Because the angle one is simple enough that you guys can write out an explanation for that on your own. Okay, so some things that we do know, we know that these two angles are equal. And we know that these two angles are equal. We were told that. But that means that these two angles are going to have to be equal because they add up to a right angle triangle, and here they add up to a right angle triangle. So what I want to do is show that, I should really have names on this. So P's up here, B, A, Q, R, D, S, T, and there's C. So what I want to show is that RQD is going to be equal to the orange angle as well. That's orange angle plus the red angle is equal to 90 degrees. Well, we have a 90 degree here, and the sum of the angles in a line are 90 degrees, so this should also be the orange angle, and this should be the red angle. This angle here, I think we can just have to call it the blue angle. You know what? We have actually a ton of similar triangles, because this one here is a 5-4 triangle. We have a bunch of triangles that are similar to 5-4-5. Or not 5-4-5, 3-4-5. Again, not writing this as a formal proof right now, just chasing pictures around my diagram. So the one opposite the 3, or no, the one opposite the 4 should be the orange one. Yeah, so there goes the orange one. The red one goes here. So I don't really care about the blue angle because opposite angles here at this intersection mean that we have the same angle there. So that would be a way to show that they're isosceles triangles. So a lot of similar triangles in here would definitely do it. Let's try it a different way using the Pythagorean Theorem. So we'll redraw our picture. It's always nice if you can do a question multiple ways. So I know this length is 25. This is 7, which I don't really need. This is 24. 12. P, T, C, R, Q, D, S. So we know we have a right angle up there, and we have right angles here. Actually, let's not do that. So this one, we're actually going to write out a bit of our explanation. The angle one, that's just diagram chasing that I'm not going to really write out rigorously. So I know AB GS is a rectangle. So AS is equal to BT, which is BP plus PT, which is 12 plus 12, which is 24. Okay. Now AD, well, that's split up as AS plus SD. So that's 24 plus 9 1/3. Well, we can write that all together. That's 72 over 3 plus 84 over 3. No, not 80, 84, 28. My mistake. Alright, so 72 plus 28, that's 100. This is 100 over 3. And that's our bottom length down here. We'll put it in purple. And we'll say let QR be X and let RD be Y. What we want to do is show that X is equal to Y. So we want to show X is equal to Y. Okay. Well, triangle ADR is right angled. So by the Pythagorean theorem, we know that AR squared plus, no, that's the hypotenuse, sorry. AR squared is equal to AD squared plus DR squared. So that's 100 over 3 all squared plus Y squared. And this is going to be 25 plus X squared. Okay. Well, the left-hand side, we can FOIL that out. We'll get 625 plus 50 times X plus X squared. is equal to 10,000 over 9 plus y squared. Okay. It doesn't look the greatest from right here. But let's treat y as though it's a constant. And we'll put everything as a quadratic in x and see what happens there. I'm definitely preferring the angle chasing method right now over this, because this is actually requiring some real explanation. As plus 625 minus 1,000 over 9. Let's combine these two while we're at it. 625 minus 10,000 over 9. That's going to be negative 4375 over 9 minus y squared is equal to 0. So now I should probably be using the Pythagorean theorem for all this. Okay. Or not the Pythagorean theorem, the quadratic formula. Wow, I'm off today. Must be the mutton chops. Alright, so x has got to be equal to negative b, so 50 plus or minus square root of b squared, so that's 50 squared, so that's 250, minus 4ac, all over 2a. So we can take out a factor of 4 from everything under the bracket, so it'll come out as a 2 here. 2,500 divided by 4 is 625. These will become pluses. All over 2. So now the 2's will cancel out. We won't have to write this as a fraction anymore. So it'll be 25 plus or minus. Now what's 625 plus 375 over 4375 over 9? Well, wouldn't you know it, that's 10,000 over 9. It's sort of like we reversed this step over here. Plus y squared. And now I am thinking I'm officially stuck. Yeah, I'm definitely not liking what I've got so far. Is there a way to salvage this, or are we stuck and we have to use the angle method? I'm not seeing a way to do it. So I'm calling this as a dead end right now, just because I don't want this video to take forever. So we're going to ignore all this, and what we're going to do is we're going to, because you guys deserve a nice, neat, written solution, we're going to actually write out the way to do it with the angles. Sadly, it doesn't use the information we learned in the C part of the question, but that's okay. Small price to pay. And let me know in the comments if I made an arithmetic error or something, because I really would have thought that Pythagorean method would have worked. Calculation intensive, yes, but I still thought it would work. There's Q, T, and S here. Okay. So to show QR is equal to RD, it suffices to show that RQD is equal to RDQ. So that is the triangle is isosceles. Okay. So let's just write in the angles that we're going to use. So we have this little red one here, this little red one here, this little red one here, and this little red one here. And we have our orange angle here, 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 and here. Okay, those are the angles we're going to be using. So we know angle TPQ is equal to angle SDQ. We see angle RDQ is going to be the full 90 degrees that's at this angle, minus the angle QDS or SDQ, however you want to say it. But of course, that's equal to angle DQS. The orange one. Okay. So, the angle APB is equal to 180 degrees, the full line segment, minus APQ minus QPT, which is equal to 180 minus the 90 that we know we have there, minus angle QPT. So that's 90 minus angle QPT, which is equal to angle PQT, which is equal to angle DQS. Okay, so again, that's the orange angle. Now, since B has a right angle, actually, we don't even need the B has a right angle. And we don't even need this calculation back here. Silly me. I'm all kinds of extra work today. So 12, 9, 15, 25, and 20. Now, since AQ over PQ is equal to 25 over 15, which is equal to 5/3. And AP over PT is 20 over 12, which is equal to 5/3. And PQ over TQ is 15 over 9, which is also 5/3. We see that APQ is similar to triangle PTQ. So angle AQP is equal to angle PQT, which, as we remarked, is the same as, oh, it's not, we haven't remarked this yet, but, which is the same as angle DQS, which is equal to our dq by our previous comment up here. So these are, again, that friendly little orange angle. But AR and TS intersect at Q. So opposite angles should be the same, so that's AQP should be the same as angle RQD. Shouldn't be TS, it should be PD here. So RQD is equal to AQP, which is equal to PQT, which is equal to DQS, which is equal to (90 minus SDQ which is equal to the other angle that we want, which is RDQ. So since we've shown that the angles are equal, that tells me that RQD is isosceles, and therefore RQ is equal to RD, exactly as we desired. So I do apologize because I sort of dismissively did the angle method and went on to try this Pythagorean thing. It might work out. I don't think there's enough information to actually make it work out, which is a bit of a shame. So then I had to abandon that and actually write up nice and, well, not neat, but nice, and with all the explanations intact, the angle method, so that you guys have a full proper solution. So that took a lot longer than I was expecting, but that's the D part, and that's the last part of question number 3 on the 2011 Galois paper. So thank you guys for joining me, and we're going to take a look at question number 4, which is the last question on this contest, in the very next video. So I'll see you guys then, and thank you for watching.